Okay, so this is the proof that square root of 2 is an irrational number and the proof that there are infinitely many prime numbers. Now, what's interesting about these is they're mentioned so often as good examples. I like to mention to my classes G.H. Hardy, who was one of the greatest mathematicians of the first half of the 20th century, wrote a book called Mathematicians Apology, which I really recommend. It's a very short book and it's really interesting. You can read it in an afternoon, and I recommend that anybody does. And in that he says, basically he's saying, look, I've spent my life being a mathematician, being a pure mathematician. Was it worth it? What have I achieved? And he talks about things being mathematically beautiful and, an idea being beautiful in the sense that mathematicians talk about beautiful ideas. And he says, look, it's difficult because a lot of those beautiful ideas require a lot of knowledge. You'd have to work for a long time to get enough knowledge to understand those ideas. But I can give you a couple of examples, and those are these ones. And he says something like, if you can't see how brilliant these ideas are, then maths is just not going to be interesting to you. He holds these up as really the excellent bits of thinking. So, these are pretty exciting proofs. They're pretty clever things. I think if you've seen these and you don't see why they're clever, then perhaps just stop and think again. Imagine if nobody had ever thought of this before, how smart it is. What a great moment it must have been when someone said, oh right, okay, this is the answer, this is the reason why square root of 2 is an irrational number, or there are infinitely many prime numbers, and so on. What I would say is, when you come into the exam, make sure you have a way of writing these down. Okay, make sure you have a standard way of writing them down, because if they ask you, you want to just be able to put it down for a few marks and not worry about have you put in all the stages and does it make sense and things. But for now, I'm not going to worry about writing it down because I get to talk to you, so I'm going to I'm going to explain it by talking. Make sure that you know how to explain it in a written form as well. I'm going to start with the proof that there are infinitely many prime numbers, because it's sort of, well, I always think it's easy, but there we go. So, it's a proof by contradiction. The statement we're trying to prove is there are infinitely many prime numbers. What's the opposite of that statement? Well, the opposite of that statement is we will assume there are finitely many prime numbers. We're going to assume there are finitely many prime numbers. And if there are finitely many prime numbers, then we can write them down in the list, right? How many? If there are finitely many, we can say how many? Well, there are n. I don't know how many n is. It's going to be a pretty long list, but I can write it down. And I can say, well, it's prime number 1, prime number 2. Now, these don't have to be in order. This doesn't have to be the smallest, the next smallest, and so on. This can be any ordered list. It doesn't really matter. But if there are infinitely many prime numbers, I can write them down in a great big long list. P1, P2, P3, up to Pn. Okay? Now, here's the clever stage. We're going to do something that, if you've never seen this before, you'll think, well, what's the point of doing that? And in a minute, you'll see why we did it. So, Euclid thought to himself 2,500 years ago, I'm going to take all of those numbers and times them together. Prime number 1 times prime number 2 times the third prime, prime number 3, and times them all together. And then, times them all together, and then add 1, okay? And that number there, all the primes times together, add 1, I'm going to call that number n. Now let's think about this number n. We know that if you have a number, a whole number that's positive, you can break it down into a product of prime factors, okay? So this number n, I must be able to break it down into a product of prime factors. Or, it's already a prime number. So, if n is already a prime number, then we missed a prime number off the list, didn't we? N is not one of these prime numbers, because it's bigger than all these prime numbers. So, one possibility, n is prime. Well, if n is prime, then we found one more prime number that's not on this list. Well, if we found one more prime number that's not on this list, then there aren't n prime numbers, there are n plus 1 prime numbers. And if there's n plus 1 prime numbers, then we can do the whole argument again and again and again. And that shows that actually, however many prime numbers there are, you haven't got the full list, there's always one more. And well, that's what infinity is, isn't it? You've never got the whole list, there's always a bit more. Well, that's infinity. So option number 1 is n is prime. That would do as a contradiction. Option number 2, so we've not quite finished yet because n might not be prime. Maybe n has got prime number factors. Maybe n is a composite number. Now, if n is a composite number, what are the prime number factors of n? What about this prime here, prime number 1, the one that we labelled as prime number 1? Is that a factor of n? Well, it can't be, because I know that that prime number there is 2 or more. okay, because all prime numbers are 2 or more. We've said 1 isn't a prime number, so if that's 2 or more, well, that prime number there divides into this bit. It's a factor of this number. So if I add 1 to this and I get my big N, then prime number 1 can't fit into it, because this number is 1 more than a number in the prime number 1 times table. Okay, so prime number 1 is not a factor of n. What about prime number 2? Well, same argument. Prime number 2 fits into this number, so it can't fit into 1 more than this number, and prime number 3 can't fit into it. In fact, if n is a composite number, none of the prime factors of n are in this list. So if n is a composite number, then there is another prime number which is not on our list. So either n is prime or n is composite. Either way, there are primes missing on our list. Okay? Well, we started by saying if there are finitely many primes, we can write a list of all of them. And with that assumption, we've ended up with there are more numbers than there are on a list. However many numbers there were on the list, there are always more. And that is the same as saying there are infinitely many prime numbers. Okay, so that is the end of our proof. That's the first one. Next one, proof that square root of 2 is an irrational number. So, an irrational number. A rational number is something that can be written as a fraction. Okay, what is a fraction? It is a whole number on the top, a whole number on the bottom, and there are no common factors between these two numbers. You can cancel it down into its lowest terms. So if I started something like 15 over 30, then that will cancel down to 3 over 6, and that will cancel down to 1/2. So I can cancel it down, and I end up with the fraction in its lowest terms. So a fraction can be written as a whole number divided by a whole number in its lowest terms. Now, if we've got those numbers and they're called rational numbers, by the way, the word rational is linked to the word ratio. So a fraction is like a ratio between two numbers. It doesn't mean rational as in sort of makes sense, right? Now, these numbers that are rational, you might think, well, why is it important to say a number is irrational? A number can't be written as a fraction. If you think about the number line, so here's 0 and here's 1, how many rational numbers are there between 0 and 1? Well, hopefully you can see there's infinitely many rational numbers, because there's a half, there's a quarter, there's a third, there's a fifth, they're all rational numbers. Well, okay, maybe that's not too surprising, but let's take a little tiny gap here. You know, there's 0 and there is 1/millionth. How many rational numbers are there in that gap? Well, again, there are infinitely many, because there's 1/1,000,001th, 1/1,000,002th, and so on, right? So however small a gap you take, there are infinitely many rational numbers in there. So if you are thinking about numbers as points on a line, which is our usual way of thinking about numbers for the moment, there are no gaps on the line, right? Every gap on the line is filled up with infinitely many rational numbers squashed in there. So there don't seem to be any spaces left for irrational numbers to exist. So if we're going to show suddenly that there are such things as irrational numbers, numbers that can't be written as fractions, that's going to be, it's going to be quite a step if we don't know they exist. Now, the other thing about irrational numbers, I'm just trying to give you a really quick introduction to this here before we get onto the proof. But the other thing about irrational numbers is if you can write them, if they exist and we write them as a decimal, well, if it's a decimal that stops, we can turn that into a fraction. Even if it's 17 decimal places, we can still write that as a fraction. If it's a decimal that recurs, we can write that as a fraction. Hopefully you can remember the proof from GCSE maths that, how to write a recurring decimal as a fraction was one of those learning objectives there. So a recurring decimal we can write as a fraction. A decimal that is finitely long, we can write it as a fraction. So if an irrational number exists, it's infinitely long and there is no recurring part of the decimal. It doesn't go 1,000,000 digits and then start a recurring pattern. It goes infinitely many digits and there's never a repeating pattern. It always keeps going forever. So what I've tried to do is convince you that these things, irrational numbers, are odd things. If they do exist, they're going to cause us problems. And the story goes, and this is one of those stories that's sort of not really true, but it's a good story, that the Pythagoreans, so Pythagoras of Pythagoras theorem fame, had a group of mathematicians who lived in a sort of religious cult with him, and they would sort of, do maths, and they thought it was a religious experience when you solved the problem and thought, oh, brilliant, amazing, that's it. That was a sort of religious epiphany kind of experience. And they didn't like the idea of irrational numbers, because numbers were supposed to be these perfect things, maths was supposed to be this perfect study, and if there's an irrational number, then that sort of messes things up because they're such ugly mathematical objects. And the story goes that the person that proved the square root of 2 was an irrational number, they didn't do what a lot of religious cults might do and say, well, we don't agree with you, that doesn't fit with our dogma, so it can't be true. Because they were mathematicians, they had to follow the logic and say, yes, that is true, but we don't like it, so we will accept that it's true, but we will also take you out in a boat and throw you off and drown you. So that's the story, is the person discovered this was drowned for his trouble. Almost certainly not true, but there we go. So let's get on with the proof then. We're going to prove that square root of 2 is an irrational number, so I'm going to start by assuming the opposite. So proof by contradiction, I'm going to start by assuming that I can write it as one number divided by another, and A and B are whole numbers with no common factors. If that's true, then square both sides. 2 equals a squared over b squared. 2b squared equals a squared. And just see how short this proof is. For something that's such a big idea, and for such odd objects as irrational numbers, we can prove in moments, right, that they exist. So 2b squared equals a squared. Which means that a squared is even. Now, if a squared is even, then we know that a must be even. Well, if a squared is even, if a is even, then we can write it as 2 times a number. Let's call it m, all right? So let's take that, and what does that tell us? Well, that says square root of 2 can be written as 2m over b. Well, it's just straightforward algebra so far, isn't it? Just messing around with the algebra. Let's just keep messing around with the algebra. B times the square root of 2 equals 2m. I'll square both sides. 2b equals 4m squared. So b equals 2m squared. So, b squared equals 2m squared. So b squared is even. So b is even. So b can be written as 2 times another number. Let's call it n. Okay, well, it all seems fair enough so far, just messing around with the algebra. Don't seem to have found anything too interesting, unless we think about it this way. Square root of 2 is written as a over b. Remember, a and b can't have a common factor, but I've just shown that a can be written as 2 times an integer m, and I've shown that b can be written as 2 times another integer n. In other words, a and b both have a factor of 2. And there's my contradiction. A and b have to be a fraction. You have to be able to cancel it down to its lowest terms. They have to have no common factors, but they do have a common factor of 2. And you might say, well, fine, let's cancel it down. Let's write square root of 2 as m over n, that's its lowest terms. Well, then we just repeat this argument with m and n, and we end up with 2 times something else divided by 2 times something else. We're going to run out of letters quite soon, but we can cancel out the 2's, and then we're going to get something else, and we can cancel out the 2's. So this is a fraction which you can keep cancelling down forever and ever and ever, which is impossible, isn't it? If you think about it, every time you cancel it down, the numbers get smaller. You can't go past 0 into negatives, so you can't keep getting smaller forever. So if square root of 2 can be written as a fraction, it's a fraction that you could cancel down infinitely many times and still never have cancelled it into its lowest terms. And there is our contradiction. Okay, that's an impossible thing to happen. So so there's our proof that square root of 2 is irrational. Okay, that is everything on section 1.1.